Hello students, today we are going to study wave motion. In the chapter of wave motion, we will study wave classification, wave speed in string as well as in transverse wave with sound wave. We will learn about equation of plane progressive wave propagating in plus x direction or in any particular direction. We will study superposition of waves in which we will study interference, beats, and the concept of stationary waves where we will study organ pipes, sonometer, and resonance tubes. Also, we will study important characteristics of sound. So, let's start with the classification of the wave. Waves can be classified on the basis of many parameters. Like first, on the necessity of the medium. On the basis of the necessity of medium, wave can be classified as mechanical wave and non-mechanical wave. On the basis of direction of vibration of medium particle, wave can be classified as longitudinal wave and transverse wave. On the basis of energy transfer, wave can be classified as progressive wave and stationary wave, that is non-progressive wave or standing wave. On the basis of number of dimensions in which energy is propagated, wave can be classified as one-dimensional, two-dimensional, and three-dimensional wave. Okay, so let's start one by one. Wave theory. Here we will study classification of waves. Electromagnetic waves, mechanical waves, where medium is essential. Let's start one by one. Wave classification. Dear student, you can prepare notes also if you want. I am telling you the most important criteria on which waves are classified. First, on the basis of direction of vibration or oscillation of medium particles, waves can be classified as longitudinal, and transverse wave. Second, on the basis of necessity of medium. On the basis of necessity of medium, wave can be classified as mechanical wave, where medium is essential, and non-mechanical wave, for example, electromagnetic wave. On the basis of propagation of energy, on the basis of propagation of energy. Wave can be classified as progressive wave, and non-progressive wave, that is called stationary or standing wave. On the basis of number of dimension, in which energy is propagated, wave can be classified as one-dimensional wave, two-dimensional wave, and three-dimensional wave. So these are the major criteria of wave classification. Let's start on the basis of direction of vibration of medium particles. Okay, the first criteria. On the basis of direction of vibration of medium particles, the waves can be classified as longitudinal wave and transverse wave. Let's learn longitudinal wave. Waves are said to be longitudinal waves. Waves are said to be longitudinal waves when direction of oscillation or direction of vibration of medium particles remains in the direction of propagation of energy. Let's say if this is direction of propagation of energy, then the medium particle will move either in the direction of propagation energy or opposite to direction of propagation of energy. When direction of vibration of medium particle remains in the direction of propagation energy, then the waves are said to be longitudinal waves. The waves produced inside the liquid and gases are longitudinal waves. Waves produced inside the liquid and gases are longitudinal waves. Now, dear student, let's see about the transverse waves. Transverse waves. When direction of vibration of medium particles, when direction of vibration of medium particles remains perpendicular to the direction of propagation of energy, then waves are said to be transverse waves. Suppose this is direction of propagation of energy, and this is direction of oscillation of medium particle, upside downside. Okay, then this type of waves are called to be transverse waves. The propagation of transverse waves takes place in the form of crest and trough, while propagation of longitudinal wave takes place in the form of compression and rarefaction. Compressions are the points where medium particles remains relatively closer to each other. So density and pressure change remains maximum at compression. And rarefaction are the points where medium particles remains relatively away from each other. So density and pressure change remains minimum at rarefaction point. Dear student, whether it is a case of compression or rarefaction, in the wave motion, if we describe the graph like this, suppose this is compression, compression, rarefaction. Always remember, distance between any two consecutive compression is lambda, and distance between any two consecutive rarefaction is also lambda. Distance between consecutive compression and rarefaction is lambda by 2. Okay. So particles at any two consecutive compression remains in same phase. Particle at any two consecutive rarefaction also remains in same phase. And the particle at consecutive compression rarefaction remains in opposite phase. And the distance between consecutive compression rarefaction is lambda by 2, where lambda is wavelength. In a very similar way, when we talk for transverse waves, the propagation of transverse wave takes place in the medium in the form of crest and trough. Crest are the points where displacement of the medium particle remains maximum in the positive direction, and trough are the point where displacement of medium particle remains maximum in negative direction. Okay. Distance between any two consecutive crests. Distance between any two consecutive crests remains lambda, and distance between any two consecutive trough also remains lambda, and distance between consecutive crest and trough is lambda by 2. So dear student, this was the first criteria of wave classification. Now we will see second criteria of wave classification, that is on the basis of necessity of medium. On the basis of necessity of medium. Waves can be classified as mechanical wave and non-mechanical wave. And non-mechanical waves. Mechanical waves are the waves where for propagation of wave medium is essential, while non-mechanical waves are the waves for whose propagation medium is not essential, like light waves, medium is not essential, and mechanical wave like sound wave, string wave, medium is essential. Here medium is essential. Here medium is not required. Medium is not required. The mechanical wave can be either longitudinal or transverse in nature. For example, If mechanical waves are longitudinal means waves inside liquid and waves formed in gases are longitudinal, while the example of transverse waves are waves in string. Dear student, if we talk for non-mechanical wave, this is complete electromagnetic spectrum of light. Is example of non-mechanical wave. Now let's talk for the third classification. On the basis of energy propagation, on the basis of energy propagation, on the basis of energy propagation, waves can be classified as progressive wave and non-progressive wave. Non-progressive wave. Non-progressive or stationary or standing wave. The progressive wave can be longitudinal and transverse in nature. Progressive wave can be mechanical or non-mechanical wave. Progressive wave can be one-dimensional, two-dimensional, and three-dimensional wave. 1D, 2D, and 3D. And what about non-progressive wave? Non-progressive wave is a wave which is formed in the bound medium, and progressive wave is formed in open medium. They are formed in open medium. And the non-progressive wave is formed in bound medium. The non-progressive wave can be longitudinal or transverse. Non-progressive wave can be longitudinal or transverse. So dear student, this was the third criteria of wave classification. Now let's discuss the fourth criteria. We can say waves can be classified on the basis of number of dimensions in which energy is propagated, like one-dimensional wave. The waves produced inside the liquid is one-dimensional wave because direction of propagated energy takes place only in one dimension. While waves produced at the surface of liquid, that is called ripple, that is two-dimensional wave. And for example, sound wave and light wave is a case of, is an example of three-dimensional wave. Energy is propagated in the three dimension. Okay, so that is three-dimensional wave. So dear student, this was the general criteria of wave classification. Now we will see how the speed of wave is determined in a medium. speed of wave. Speed of wave in string is written as V equal to under root T upon mu, where T is the tension in the string and mu is the mass per unit length of the string. T is the tension in string and mu is the mass per unit length of string. What is mass per unit length? Mass is volume into density. This is mass per unit length pi r square, where r is the radius of the wire, rho is the density. Now if we talk for speed of wave in sound, the general formula is V equal to under root E upon rho, where E is modulus of elasticity of the medium, where E is the modulus of elasticity of the medium, and rho is the density of medium. E is modulus of elasticity and rho is density of medium. Okay. Now dear students, let's talk about the speed of sound in solid, liquid and gases separately. Speed of sound. If we talk for speed of sound in solid, for solid, modulus of velocity is determined or is written as Young modulus of velocity. So in case of solid, we write speed of sound as under root y upon rho, where y is Young modulus of velocity where y is Young's modulus of elasticity. Its unit is Newton upon meter square in SI system, and dimensional formula is m L minus 1 T minus 2. Now if we talk for speed of sound in liquid, if we write speed of sound in liquid, we write in case of liquid, modulus of elasticity is given as bulk modulus of elasticity. Which is written by letter B. This is speed of sound in liquid. Now if we talk for speed of sound in gases, in the beginning, the propagation of sound was assumed to be isothermal by Newton, but this was proved to be wrong. This was according to Newton, where propagation was assumed to be isothermal. And isothermal bulk modulus of velocity is written as pressure. Now later on, it was modified and the process was assumed to be adiabatic. and adiabatic bulk modulus of velocity is gamma p. This was corrected by the Laplace. Process was assumed to be adiabatic. So dear student, now we will be solving any problem for speed of sound in gases by assuming process to be adiabatic. Okay. So speed of sound in gas, we will use the formula V equal to under root gamma P upon rho. And what is density? Density can be written as mass upon volume. So this formula can also be written like this. Gamma RT upon M. M is the molar mass and T is the temperature in Kelvin. So from this expression we can easily say speed is proportional to under root temperature. If we plot the graph between speed and square root of temperature, this will be straight line. If we plot the graph between V and temperature, V square proportional T, so graph will be parabola. And if we want to solve any numerical problem when molar mass remains constant, so you can write V2 upon V1 equal to under root T2 upon T1. But never forget to write temperature in Kelvin, okay? And how you will convert T degree centigrade equal to T plus 273.15 Kelvin. This is the way to convert Celsius into Kelvin. This is the way to convert Celsius into Kelvin. Now, dear student, if temperature change is small, when temperature change is small, then you will be using this formula like speed of sound at 0 degree centigrade. You will be writing as gamma R 273 upon M. And speed of sound at theta degree centigrade, you will be writing gamma R theta plus 273 upon M. If you want to make general relation between speed of sound at 0 degree centigrade and theta degree centigrade when temperature change is small, so dear student, divide these two equations, speed at theta degree centigrade divided by speed at 0 degree centigrade equal to what? This is theta plus 273 divided by 273 under root. This can be written as 1 plus theta upon 273 power 1 by 2. When a small change in temperature there, you can expand this by binomial expansion 1 plus 1 upon 2 theta upon 273. After solving the equation, speed of sound at 0 degree centigrade is approximately 332 meter per second. So speed of sound at theta degree centigrade will be approximately this formula. You will be using this formula, where theta is the change in temperature. Theta is the change in temperature, okay? This formula is valid when temperature change is very small, like not more than 10 degrees centigrade, not more than 10 degrees centigrade. Then you can use this formula. Like if temperature increases by 1 degree centigrade, if temperature increases by 1 degree centigrade, then we can say speed of sound will increase by 0.61 meter per second, 0.61 meter per second, okay? Remember, speed of sound at 0 degree centigrade, this is 332 meter per second. Now, what is effect of density on speed of sound? Effect of density. Dear student, we is under root gamma p upon rho. So when humidity increases, density decreases, and when density decreases, speed increases. This is the effect on speed of sound. Okay. What is effect of pressure on speed of sound? Dear student, there is no effect of pressure on speed of sound until temperature changes. No effect. Okay. There is no effect. Why? This is gas equation PV equal to nRT. N is number of mole. N equal to mass upon molar mass. This is RT. So P is what? M upon V, M RT. M upon is V is what? This is density. So you can write P upon rho equal to RT upon M. So there is no effect of pressure until temperature changes, okay, on speed of sound. Now what about what happens when frequency changes? Effect of frequency. On speed of sound. Effect of frequency on speed of sound. Dear student, in the formula V equal to under root gamma P upon rho, there is no term like frequency. So there is no effect of frequency on speed of sound. There is no effect. No effect. Had there be some effect of frequency on speed of sound, we could have not enjoyed our orchestra program. Okay. So dear student, this was all about how to calculate speed of sound in a medium. In the next lecture, we will be seeing, we will look equation of plane progressive wave propagating in particular direction. Okay, thank you.